Good afternoon, everybody. Welcome to the Manning Publications Twitch stream. My name is Matt Groves, and we're going to get started here with a presentation. And I've got some great code. Well, I'm not calling them great. I'm going to call them adequate code samples for you later on today in the stream. And so if you're here in the chat, just say hello. I just want to make sure I can monitor the chat as we go. I don't normally take over streams like this. I normally stream on my own, which is at Twitch/Matthew D. Groves. So I'm going to pull up the Twitch feed on my phone here just to make sure if any chat messages, any questions come in, I will see them and respond to them in a timely fashion. Let's get on with it, shall we? So here we are again. It's a new project or refactor, and you've reached the point where you need to select a database. You take the blue pill. You stick with the relational database you've always known, and the story ends. You believe what you want to believe about NoSQL. You take the red pill, and you go down the NoSQL rabbit hole and see how deep it goes. And there's a lot of reasons that most of us still take that blue pill over and over again. And maybe it's a good reason. Maybe because it's the right tool for that particular project. Or maybe it's because the corporation says so. Everyone's got to use the same database. Or maybe it's because when we researched NoSQL 4 or 5 years ago, it was just not there in terms of features that we needed, features that we wanted. Maybe it's because we really like the SQL language. And yes, those people are out there. There's quite a lot of them that like SQL, and we don't want to give that up. We like SQL. And maybe the reason is because, and this is what I want to focus on today, although I'm happy to talk about those other things if you have questions in the chat, is I want to focus on ACID transactions. Looking at NoSQL, there's no ACID there, so how could it possibly be any good? And the response from advocates like myself, NoSQL advocates, has been something like this. Don't try and bend the spoon. Don't treat NoSQL like it's relational, because there is no spoon. And you probably don't need transactions. And I do believe there is some truth to that. I'm going to talk about that today. But what if I told you that many popular NoSQL databases have ACID transactions right now and have had them for a while? So today I want to take you inside of a sparring program. I want to talk with you about what ACID actually means. I want to talk about the challenges of doing that in NoSQL, specifically distributed NoSQL. I'm going to cover the reasons why ACID transactions may not be as big a deal as you think, but I'm also going to show you what ACID means and how NoSQL databases have been adding transactions to a distributed NoSQL database architecture. I'm going to dive deep specifically on one of them, Couchbase, because I have some specific knowledge there, and I think it's also a very remarkable approach that kind of is different than the others, and it really helps demonstrate the trade-offs between the couple of different approaches there are. So you're going to learn the kung fu of ACID, Mr. Anderson. These are questions I often ask myself. Who am I? Where am I? So I put a slide in my deck just so I don't forget. I'm Matthew Groves. I'm a developer advocate with Couchbase, so you can see that's why I have some special information about Couchbase, and I'm a little biased as well, so just keep that in mind. I'm a Microsoft MVP, a Pluralsight author. I'm not listed on here, but I also wrote a book with Manning a while ago, and not related to this topic, but AOP and .NET. It's a book I'm very proud of, so I'm not going to talk about AOP today, but it is out there. I'm also part of a great family. I'm here on Manning's Twitch feed. They were gracious enough to let me take over their Twitch stream for a while. If you're watching this video elsewhere, recording or something, definitely go Twitch/Manning Publications, hit that follow button, hit that subscribe button, everything you like to do there, and you'll be notified about other great speakers who take over this channel and other great the conferences that Manning puts on, basically one day like mini conferences all around a specific topic, which I was grateful to be a part of one about Kubernetes recently. Also, before I get going here, I just want to make one little comment. So I mentioned Couchbase here. Couchbase is not CouchDB, not the same thing, so don't get that confused. It's a very common point of confusion. I just wanted to knock that out of the box right away. Here's what I want to cover today. We're going to talk about transactions in relational. Hopefully a bit of a review, but it's always good to sort of level set so we know we're on the same page there. Once I've covered that, I'm going to do, again, hopefully maybe a little bit of review, or maybe if you're brand new to NoSQL, it's not a review, but why? Why NoSQL? Why does it exist? What problems does it solve? Why do people use it? And then we'll get into the ACID stuff. Specifically, what does ACID actually mean? And so basically the point here is not just about transactions, but why is it hard? And why is it even harder with distributed databases? Then I've got a demo for you. I'll just be demoing a transaction in NoSQL database, which doesn't sound all that exciting, but I think it's really, really impressive given how far NoSQL has come in such a short period of time. And at the end, I've got some other links and resources. I can also take questions there at the end, but feel free to drop questions in the chat room at any time. I'll try to monitor the best I can, answer those questions right away as soon as I see them. You don't have to wait till the end for that. All right, so let's talk about transactions in relational. So in relational databases, this is SQL Server, MySQL, Oracle, and so on. There's something called third normal form, and that is basically the way that we design and model data in relational databases. So even if you never heard that term before, third normal form, if you're using one of those databases, you're almost certainly designing this way. So I'm not going to go into all the details here about what that means. And you know, for those of you who do know what it means, you may even be Boyce Codd normal form, or maybe even fourth or fifth in some situations. Point taken. But third normal form at least is what we designed for. And so part of third normal form is that it must be second, and then second must be first, and so on. So it's like increasing strength. Now this table here on the screen, this one is, that is not even in first normal form. So we've got this repeating group here, item 1, item 2, item 3. And so intuitively, you probably see what the problem is with this approach. And what if I want to buy more than 3 items? Well, then I have to add item 4 and item 5 and so on. And if I buy less than 3 items, then there's just sort of these blank spaces that are just kind of taking up room in the table, but they're not really storing anything. So that's just kind of awkward. So the more correct design, I'm not saying this is always, but almost always, the correct design for this is to split that single table into multiple tables. And so then each item, instead of having a column, it gets its own row in a separate table. And there's a foreign key there, which is, you can see the cart ID, and that points to the row it belongs to in the other table. And so this is the typical design, and this is the way you would go from first normal form to second and third and so on. And so because of that, we've now split the data into multiple parts, multiple pieces, multiple tables, multiple rows. It's all split up in different places. And so therefore, if we want to save a shopping cart, we have to, all those different pieces, we have to treat them as if it's one operation or one thing that's all together. Either all succeeds or all fails. So this is how it would work. We'd say, okay, I'm going to start a transaction. I'm going to insert one row into that shopping cart. Okay, there we go. There may be more data there, but just the date and the ID is enough for now. Okay, let's insert a row into shopping cart items, and that corresponds to that shopping cart we're creating. So it's foreign key there is 100, and it's the phone case. We have a second item in the shopping cart. We'll insert that as well as a charger cable, also corresponds to the same cart. And finally, we say, okay, I'm done creating the shopping cart for now, or modifying the shopping cart for now. Go ahead, database. You can take everything and what's called commit that, and actually put that in your database for other people, other processes to use. Okay, that's how it works. Hopefully, most of the time, but sometimes things can go wrong. So let's see what happens in a different case here. We're going to do the same sort of operation. Insert a row in a shopping cart. There it is. Insert a row into shopping cart items. Oh, what's this? Oh. I've seen that before. That's the blue screen of death. So something crashed there. Something went wrong. Maybe it was the database server crashed. Maybe it was the application crashed. Something crashed. And so we're halfway through the transaction. So the data is left in this inconsistent state. We've got the shopping cart, but none of the items. So just like this empty shopping cart floating around out there. But if this all takes place inside a transaction, no problem. If the database itself crashes, again, not a problem because it wasn't committed. So the database never marked it as, this is done. I'll just go ahead and assimilate this data. If something else went wrong in our program, maybe an exception or something like that, that's okay. We can detect that. We can catch the exception, and then we can instruct the database through a command called rollback to say, hey, forget everything I just said, database. Just go back to before this transaction. This doesn't count. Give me a do-over. Now, one more point here before I continue. Oh, and by the way, so the data gets rolled back there. Before I can continue, I want to think back to that first table that I showed you with the, it was all in one table with the item 1, item 2, item 3. If we had our data modeled that way, we wouldn't need a transaction because it would just be one operation to put data in there. Now, I'm not saying it's a better design for that. It's still not a good design because we have all those extra gaps and we have to define, n number of carts. But we wouldn't need a transaction. Okay, now let's switch over to a NoSQL document database. Now, the short story here is that data is not stored in rows in a table. There's no tables, there's no columns, nothing like that in a document database. The data is instead stored in individual pieces of JSON called documents. So there's 4 documents here on the screen. And so the top one is a shopping cart, and the other 3 are items in the carts. Now, my background is relational. Before I worked at Couchbase, I did a lot of stuff with relational databases. So this might be my approach. If I'm first trying out a NoSQL database, a document database, I might try the same approach and say, let's just put all the data in individual pieces like we did in relational. Or maybe it's because I'm importing from a relational database and the data is already split up like this, so this is just the way I get the data. Or maybe it's just because this is what I know. It should work the same everywhere, right? Now, if this is what you're thinking with NoSQL, and then you hear, oh, but there's no ACID transactions. You can't do that with NoSQL. Well, then, yeah, no kidding. This is not going to be a good approach for you. To model it this way with no transactions is just going to be a mess. I don't want to do that. And so I think a lot of people were turned away or turned off by NoSQL databases because of this particular issue. But we aren't using tables anymore. There's nothing that says we have to put our data in third normal form. In fact, since we're using JSON, we have support for arrays and nested objects in a single piece of data. So we don't have to define item 1, item 2, item 3. We can just say there's an items array and put all the items in there. And it's just strings in this case, but it could be a more complex object. So if I create a shopping cart and model it this way, there's only one document here. So there's only a single operation on a single piece of data. And so voila, we don't need a transaction. We can have an ACID guarantee on a single document. As long as we're only working with one document, we're totally fine. We're totally in the clear. So if you can model your data this way, if you can aggregate it and consolidate your data into a single document instead of a bunch of pieces and multiple tables, then you no longer need an ACID transaction. And this is kind of the story that, like I said, advocates like me have been saying over the years. It's not as big of a deal as you might think. Now, if you've heard of the concept of aggregate root before or read this book, Domain-Driven Design, by Eric Evans, that's basically the same modeling exercise here. We're sort of combining the data down, we're aggregating it and consolidating it to the aggregate root. So as much as possible. And you can't consolidate everything down into one document, but you can consolidate, a single aggregate root and all its auxiliary pieces of data into a single document. And I'm not the first person to make this observation. So as far back as 2012, and I'm sort of blocking the link here, so let me turn myself off for a second. So as far back as 2012, Martin Fowler actually did a lot of writing and presentations on NoSQL databases, and he preferred the term aggregate oriented in place of document or key value for this exact reason, because we're storing data in its aggregate instead of in its individual components and pieces. So if you want to check out, this is a great video on it here. This is bit.ly/Fowler AGG, capital A. So you can learn more about that. And Martin Fowler's a great speaker, so I highly recommend that video no matter what. Okay, so we've talked about modeling and why maybe transactions, maybe not such a big deal. So if that's the case, if I'm in the NoSQL world, or I'm still considering it, then why would I want to use NoSQL? What benefits does it have for me? So here's what I call the big 4. And these are the 4 kind of biggest reasons you might use NoSQL. There's other reasons beside this, but these are kind of the big 4 that really made it catch on. So the first one is scaling. And I believe that that's kind of the main driver for NoSQL originally. And still to this day, actually. Scaling is hard to do with systems that were designed to run on one machine. and serve a relatively small number of operations, like your traditional relational database. And so now I have to serve this data up to a website, and I'm serving millions of operations. And now if I'm still on one big machine, this becomes very expensive. I have to buy a much more expensive machine to handle this, or a much bigger VM in the cloud provider, for instance. Or it becomes impossible in some cases to serve that many records from one machine. So then what scaling actually means to me is that it should be distributed amongst multiple machines that all act together in what's called a cluster. And so it should be easy to cluster those machines together. You shouldn't have to jump through a lot of extra hoops to do that. And sharding of data, which is basically just taking all the data and splitting it into just different groups, different shards. So you can put a shard on this machine, a shard on this machine, etc. And that should be, again, built in. It should be automatic. Now, in practice, this varies from solution to solution. Depending on which NoSQL solution you look at, they may not have been designed with scaling in mind. You may need to configure your own load balancer in some situations. You may need to configure leader election and sharding definitions and all this stuff. And that just becomes a lot of extra hoops to jump through for some systems. It also makes transactions become much more difficult because now the network is in play. So if I have a shopping cart, or let's just say a piece of data here and a piece of data on a different machine, do I have to lock both machines basically? And so, I mean, that becomes very difficult to do. So that's the A in ACID, atomic. Availability, or high availability, I should say, is another huge benefit of a database that's designed to be distributed. So let's think back to that one big server model again. If that one big server just goes down, someone trips over a power cord, or entry-level developer runs a really gnarly query on it and just takes down the whole machine, the whole system goes down. Anything that depends on that database goes down. But if you have multiple machines in a cluster, if one of them goes down, the other servers can recover. And there's different models of this, but they can recover, and there's very little or no downtime. And again, in practice, depending on which solution you look at, this might involve a lot of extra setup. So again, with the sharding, you may have to set up internal and external replication processes, something like Zookeeper to kind of manage all the different machines in a cluster, etc. So again, a lot of work to jump through for some systems. Performance, so every database claims superior performance, of course. Why wouldn't they? And they all publish benchmarks to back it up, of course. Why wouldn't they? But they can't all be right. So we've already seen an example, though, of how data modeling and consolidation can reduce the total number of operations. So in relational, it might be 4 operations. With a document, it might be 1 operation. Additionally, many NoSQL systems, not all of them, but many of them, introduce some kind of additional memory focus. So it's either memory first or memory only in some situations. So you don't have to wait on the disk, or you don't have to wait on the disk as much. Now, this also factors into the lack of transactions, because there's the D, the durability. And we'll talk about durability and what that means later. And the last one, which is a lot of the benefit people talk about now, I don't think this was really the primary goal of NoSQL in the early days, but it is a very nice side effect, or to some people, unfortunate trade-off, depending on who you ask. But with flexibility, with a distributed database, each piece of data has to be isolated, has to live on its own. It can't live in a table, in a column, has to live completely on its own. So therefore, it can be moved to any of the servers in the cluster. So since it's already independent, we may as well do the best we can and put it into a well-known, well-understood format. And in most cases, that means JSON, because there's JSON parsing libraries in just about every language and platform you can think of. So it's a very nice format for us to use. We get arrays and nested objects and such. So again, I'm going to focus on document database today, but another key tenet of NoSQL is something called polyglot persistence, which just says use the right database for the job. Don't use the same database for every single service, every single task. And this is especially good in a distributed architecture or a microservice architecture, where each service may want or may need different kinds of data structures. So for instance, graph, search, like text search, time series, document, which I'm going to focus on today, mobile synchronization, and then of course relational might be in there as well. So that flexibility is a very nice thing to have in many architectures. So I've already touched on some of the reasons why ACID is hard. I mentioned durability, I mentioned atomicity. I want to run down what ACID actually means, just as a little bit of a review here. And because, to many people, ACID just means transactions, but that's really not the case. So ACID is a set of properties to describe databases. This was coined back in 1983. It's not a standard. There's not a governing body or anything like that. So it's really just kind of a term that's been coined, and there's a lot of nuance, and it's sometimes difficult to get two developers or two database people to even agree on what it means all the time. So from my point of view, it's really more about having a conversation than it is about compliance. So if someone claims ACID compliance, something like that, then you got to really look up, well, what does it actually mean by, what are they complying to? So if you are familiar with ACID, then I fully expect you to disagree with my characterization. That's totally fine. I mean, at least partially. But if you do have some familiarity with it, feel free to chime in the chat or ask questions. Happy to discuss that deeper. This is just kind of a 4 or 5 slide overview of it. So A is for atomicity, and this is important for transactions because a group of operations either all succeed or all fail. And if we're only talking about one document or one piece of data, then you get atomicity because it's going to succeed or fail by itself. But think back to that shopping cart example. In a relational database, if you can model it this way in relational, you need a transaction. If you can model it down to a single document, you don't need a transaction. So at a single document level, a NoSQL database can have atomicity and still not have transactions, by the way. C is for consistency. This is, in my view, maybe the most nebulous part of ACID. So here's some of the things you might encounter when you talk about consistency. So dirty reads, dirty writes, so-called phantom reads. Basically, it says that data is not going to ever appear to the user to be in an invalid state. So back to that shopping cart example. If an operation can't be rolled back and that blue screen happens, then the data is in an inconsistent state. We wanted to put in a shopping cart with 3 items, but we only have now an empty shopping cart. And there's other things that might fall into this category. So with relational, you can't put 6 columns of data into a 5-column table. That's just not consistent with what you defined. A document database that requires JSON, you can't put non-JSON data or invalid JSON data into a JSON document. So you got to close all your curly braces, that kind of thing. The other thing people bring up a lot is this idea of eventual consistency. And sometimes this is a butt of a joke that, oh, Twitter is not eventually consistent. That's why my tweets aren't showing up or something like that. But what eventual consistency describes is a situation where the data you retrieve may be stale. It may not be the latest copy of the data. So maybe missing some data or have some old data, something like that. And eventual consistency depends on a number of factors. And again, this varies from database to database. So I'll just take an example in Couchbase. In Couchbase, there's more than one way to read and write data. So Couchbase has a key value API. It has a SQL API. It has full text search, all these different things. And so if I decide to use key value to insert a document or update a document based on its key, and then I turn around, another process turns around and uses the key to look up that data, it is always going to get the latest data, period. There's not going to be any eventual consistency. It's a strongly consistent distributed database in that sense. However, if I insert some data and then I go and use a SQL query to try to retrieve that data, if I try to do it immediately, I may get some stale data or I may get the latest data. Because the SQL query now has to depend on an index, and that index gets updated asynchronously. So I can, as a developer, I can say, give me, I'm okay with stale data, just give it to me as fast as possible. Or a developer might say, I need the latest updated data, so wait for the index. And so as a developer, I can have latency preferences on my query. So it gives me some sort of knobs to play with and say, well, which way do I want to go with this? Do I want it as fast as possible, or do I want it to be as consistent as possible? And again, check your database to see what the options are here in terms of stale data and consistency. So if there's potential for stale data, this is kind of one of the things that bit me when I very first started out with Couchbase. I was inserting some data and then querying it. I was like, why isn't it showing up? If I hit refresh, it shows up, but it's not showing up right away. Well, that's because I wasn't quite aware of that eventual consistency concept. And speaking of consistency, this is what's known as the Jepson consistency model map. And it's a lot to take in, and I'm kind of covering up some of it. It's not super important, but there you go. And there's 3 different colors here. Hopefully it's relatively obvious, even if you can't see the entire spectrum. There's 3 groups here. So kind of these over here, these orange ones. And then up at the top area up there is the pink ones, and then there's blue in kind of the bottom left and left over here. So I'll cover these groups. I'm not going to go into each one of these individually. There's a lot to cover there. But pink are the models that are just not possible when there is a network involved because of network failures. So if that's the case, if you're using pink and you have a network, then that means that in order to achieve those levels of consistency, you have to stop everything. And that's just not acceptable for many systems. Orange is what's called sticky available. So that works if a client is stuck with a specific server. So you have multiple servers, but each client gets stuck to one individual server. And the use cases for that they're pretty slim, so you don't see a lot of that. And blue is what's called total availability, which means even if the network goes down, you can still achieve these levels of consistency. So as you can see, it's not just, is it consistent or not, but what kind of consistency is it? And there's all these different options here, all up and down this tree. So read committed, for instance, is what you might consider stronger than read uncommitted, because it means read committed means that it's not possible for a dirty read. So if there's a transaction that's in flight right now, I can't read the data as it's in the middle of the transaction. I'm reading it either before or after the transaction. Whereas read uncommitted, I can actually read some of that dirty data that's in the process. And you're going to see some dirty data here in the demo later on. So you'll kind of get a better understanding of what read committed means. In Couchbase, actually, we say we're read committed, but there's actually some things you can do, and this is back to the multiple APIs that are monotonic atomic view. Monotonic? It's hard to say. Monotonic atomic view. So if you're using the key value API, for instance, it can be as strong as monotonic atomic view. But when using the SQL API, it's not. So Couchbase is kind of like in the middle there. So even though there's all these different levels of consistency, there's still even some nuance. So it's difficult to say, Couchbase is this level and Mongo is this level, because there is just so much nuance there. And you might look at this chart and you might say, well, strict serializable, that's the top. It's the strongest, so it must be the best. But there's pretty strong trade-offs to get that level. If a node shuts down, nobody else can do anything. And basically, strict serializable says one operation at a time. And really, that's just not a very efficient way. So you have to have a very specific use case to deal with that. So read committed, I think, is the default for many relational databases, for instance. I is for isolation. So in regard to transactions, this is very much about concurrency. So if I have one or more processes looking at the same data around the same time. So if a transaction itself is isolated, that means it should appear to anybody outside the transaction that the transaction itself is going to leave the database in the same state as if all those transactions were executed sequentially, like back to back. And even though it may not actually be the case. Optimistic and pessimistic locking is typically what this means. So if you're familiar with those terms, you can lock some data, and there's different levels, optimistic and pessimistic locks. And those have been around for, again, at the single document level in NoSQL for a long time. But for a transaction, we need to maybe lock multiple documents. And so if we do that, there has to be a timeout associated with all the locks. Otherwise, a document could be locked in perpetuity. So therefore, the whole transaction is constrained to a timeout period. Finally, durability. So I mentioned this earlier. This is a really important point to make about data durability. Is your data durable? So after your write operation, if the system crashes, will the data still be there? That's basically what durability means. And again, it's a very nuanced thing to say, is your data durable or not? Because what does, typically that means it hasn't been written to disk. And so therefore, if the system reboots, it'll still be there on disk. But there's a lot more to it than that, especially if we add multiple machines that are communicating over a network. So what if the disk fails? And disks do fail. So is that considered durable? Because the disks themselves are not durable given a long enough period of time. And what about a memory-only database? So I mentioned that earlier. For performance reasons, we might want to use memory-only. Is that not durable? Because if the system reboots or crashes, memory is lost, right? But what if there's a copy in some other machine? Like I have some friends in my cluster, and I put the copy on one of my friends' machines in their memory. And if I crash, it's still on my friend's machine in memory. So is that durable? What if the entire data center goes down? So Amazon East all goes down, and our data is going down with it. So maybe a data center itself isn't durable enough. We have to have a West and an East data center. What if the planet blows up? I hate to say a what if like that in this year, but what if we need a backup on a satellite or on the moon or something to make our data truly durable? So these are all things you have to think about. Maybe the planet example is a little ridiculous, but just trying to make a point there. And so when you save data, do you check to make sure that it's been saved to one disk? Do you even check at all? Do you just save it off and assume, it'll get saved? Is 2 disks enough? 2 other machines' memory, is that enough? 2 other disks and memory. So in NoSQL, and you're going to see this in my demo, you can specify the durability level on a per operation basis. So we can say maybe most operations are fine, just fire and forget, it'll be fine. But maybe there's some operations that are, this is based around a specific financial transaction. So we have to make sure we're going to incur the extra overhead, like in a transaction, for instance, to verify the durability. And so this is a challenging thing to do because, as I mentioned, you have all these different disks and memory and network. It's all involved. So it's challenging. Implementing ACID just by itself is already a challenging problem, but now factoring in distributed systems, it makes it even more so. So here's a few of the problems and some of the ways that I've seen them dealt with to not necessarily solve them, but to at least mitigate them. So the first one is a class of problems called split brain. And this basically means network problems. So if there's you have crashes and crashes and consensus type of thing. So what happens if one or more of the other machines on the cluster crashes? Well, the consensus requirements, right? So as I mentioned, durability. What's the acceptable number of nodes, what they're called in a cluster, for the operations and replicas to be persisted to? Is 1 good enough? Is 2? Is a majority? Is memory good enough? Do I need to have disk? Second one is uncommitted transactions leave behind artifacts. So in a read committed system, we should never see the dirty reads. But if a transaction fails right in the middle, it's going to leave some extra stuff around that we can't necessarily view unless we flip some flags and go looking for it. But most processes can't view, but we got to clean those up at some point. Otherwise, they're just going to keep taking up space. And so there's a couple of methods to deal with this. One is called the cooperative model. I want to show you this one today. This is a cooperative model applies when you're dealing with a client-side implementation of transactions. And something like Paxos, which I'm not going to go into, but it's an algorithm or a system, or something like Zookeeper can just sort of act as a controller on the server side now to say, okay, give me the transaction, I'll take care of it, and I'll coordinate among all these different pieces of the cluster. And edge cases. And this is, this is one that always bites us as developers, no matter what we're working on. But, there's edge cases to a transaction. And split brain introduces even more edge cases. So network goes down temporarily. Network goes down at n equals 1, at n equals 2, at n equals 3. Or sorry, t equals 1, t equals 2, t equals 3, etc. All those things could be different. So how do we deal with all those? And this is true from relational databases, and it's even more true of a distributed system, introducing the network. So the way to deal with this is just mitigate that. Try to identify the edge cases, test for them, plan for them, expect them, and deal with them. Or the alternative is might say, well, that's a 1 in a billion, or that's a 1 in a trillion thing that could happen. So the juice isn't worth the squeeze, as they say. So we'll just document that and say, it could happen, but it's 1 in a trillion. Latency is another issue. And this is performance, basically. We don't want to just go ahead and reinvent a relational database with the same performance constraints as relational, because we're just reinventing something that already exists. And so the challenge here is, the solution here is really educational. And so distributed ACID transactions are always going to have overhead, potentially a lot of overhead. Hopefully it's getting improved and getting reduced with every new version, but it's always going to be overhead there. And so only apply a transaction when it's necessary is basically the solution there. And then we need to understand, how does an ACID transaction affect performance, and how does it affect high availability? And I'll have some links for you later to kind of wrap your head around, okay, with transactions, you can run this many operations. Without transactions, you can run this many operations. And again, basically, we're going to solve with data modeling to reduce the transactions that we need, but use a transaction when we have to. Okay, so then correctness is also what we're talking about. This kind of goes back to the edge cases. So once we've got an ACID transaction in place, how do we know for sure that it's going to be sufficient? Have you ever written threaded code and tried to test it? Try to write a unit test for it? Even simple threaded code, writing a unit test, you're going to have to worry about race conditions, and it's just not easy. It's not straightforward. And now add the network into that. And imagine all the problems that network is going to introduce into the equation as well. And so how do we verify those edge cases, that we even know, we're even aware of the edge case in the first place? So one method is we can go to Jepsen, and we can say, hey, let's look at the Jepsen guidelines, or maybe let's even hire Jepsen to verify this for us, to go through their testing, which is a good thing to do, but they might not even catch all the edge cases, right? And this is expensive to do, especially if we want to, okay, we fix this, let's re-verify it. Well, then we got to go through the whole thing again. And you might even find yourself in this situation here. And I'm not trying to diminish a competitor here. I just want to show you that, the most popular NoSQL database in the world has even struggled to go through those Jepsen guidelines and get on the same page with them. So it's challenging work, and it's not a completely solved problem. It may not ever be. I want to talk about the trade-offs here, because I mentioned this earlier: client-side and server-side approach. These are two different approaches you can take. Let your client, let your application handle the transaction, or let your database server handle the transaction. And these are, for the most part, some NoSQL databases that I've seen so far are taking the server-side approach, and Couchbase is taking the client-side approach. So I want to compare and contrast, because again, there's not a right or wrong way to do it. They're both approaches that have pros and cons. So with the server side, the pro is here that our SDKs, we make a .NET library available, we make a Java library available for our database. We don't have to change those very much to add a transaction here. It's basically just adding some more methods like start transaction, commit transaction, rollback transaction, and those are just relaying those commands to the server. I don't want to diminish this, because it is still hard work to build an SDK and make changes and document it and so on. But the actual transaction implementation doesn't live in the client. The server is taking care of all of this. And so therefore, the cons are that the server or the server side has to do a lot of extra work. So things like a global coordinator, a global lock manager, and a global scheduler. Something to synchronize clocks so we make sure we're getting things done in the right order. And so this can be somewhat fragile, and it requires some additional configuration, and maybe even has strict requirements about your servers. Like your servers have to, match these specifications in order to support a transaction. So it's a lot of work on the server side to do that. The pros of the client side is basically kind of the reverse of that, the flip side. So we don't have to implement those global things. To the server side, to all the cluster, it's just going to be regular operational traffic as far as the server is concerned. Now, there are some features that we may need to build on the server side. So I mentioned durability requirements, staging capabilities. You're going to see some of that here in the demo. But none of the transaction logic lives on the server. So this actually makes it quick to iterate to an extent, because we don't have to wait on the server team to actually make the change and deploy it to the next version. We can just update the SDK, for instance. And so there's nothing new to configure on the server. Again, it's just regular traffic as far as the server is concerned. Now the cons here is that, one, we have to now make major SDK changes. And this is actually why my demo today is going to be in Java. It's not because I love Java. It's just because it's not yet ready in other languages yet. So all clients that use transactions must be on the same page. They must follow the same algorithm. This makes it a little harder for the community, unfortunately, to follow this approach. And let me give you an example of that. So let's say there's someone out there who wanted to build a Couchbase application, a Fortran application that uses Couchbase. So first of all, Couchbase does not have an official Fortran SDK. So right off the bat, you actually have to build that, which is a challenge in and of itself. But it's totally possible. People have built community SDKs. So for instance, CodeFusion, which you may think, CodeFusion, people still use that? Yes, they still do. And Couchbase doesn't really have the resources to hire a CodeFusion team, so the CodeFusion community stepped up and created a Couchbase SDK, right? But now let's say that Fortran client, you want to do transactions, or the CodeFusion client. Well, you have to learn about the same algorithm that the Java client, the .NET client's using, or wrap it in a proxy something else, right? So Couchbase Incorporated will do a lot of this work, right? Building the Java SDK that I'm using today, eventually deploying it to the C and the .NET SDK and so on. But it is a heavier lift to do this on the client side. Okay, speaking of the demo, I've talked about that a lot, and I'm actually going to get to it now. So let me bring up here. Let's see, bring up my notes here. All right. So this is Java on the screen here. Let me know if that's not big enough. Well, make it just a little bigger, just in case. That should be fine. Okay. I'm not a Java developer. And if you are, that should be pretty obvious to you once you start reading this code here. But I think it's still readable, and obviously because I'm a C# developer, I can still read it and work with it. So if you're JavaScript or PHP, etc., it should be fine. Just to kind of understand the concepts here. And so what I've got here is I've got a console program, very simple console program, that's going to help me track conferences and my interactions with those conferences. So as a developer advocate, I do a lot of stuff with conferences. Virtual these days, but still a lot of stuff. So I might submit to a CFP to a conference, or there's lots of emails actually with Manning behind the scenes that I'm setting up this appointment to take over their stream. And so I might want to have a piece of data that represents a Manning event, or Manning Kubernetes event, for instance. Like right here, Manning Kubernetes events. And then I have a separate document that tracks all the various interactions that lead up to, before, during, and after my presentation on Manning stream. So it might be me submitting to the CFP, me getting accepted or rejected, me delivering the presentation like I'm doing right now, answering questions, during and after, submitting my slides for someone to download the slides later. And so what I need transactions for all this, because I want the one piece of data, this main one here, to contain information about my, let's say, my latest interaction that's in here. So this is going to contain a bunch of them, but maybe I just want the latest, the latest date, and maybe I want the total number of transactions. So there's, or interactions. So maybe there's 3 in here, and I want this document to say, oh yeah, total of 3. Now I could do this with a query and a join every time, but that might be a little slower. And also I wouldn't have anything to demo today, so we're gonna go that route. Okay, let's scroll down a little bit here. So here at right here. So here at the start, these are just a bunch of some strings, not super important. It is Manning and Manning interactions, and these are just some credentials, just in strings there. Okay, let's scroll down here to main. So this part here, I'm just connecting to a Couchbase cluster. Again, not super important. It's just these are some Java objects that I need to interact with the data. Okay. Next up, I'm creating these initial documents, and I should only have to do this once, but I'm running it every time just to make sure that they're always there. So let's actually go down and take a look at this method, create initial documents. And so one document here is to represent a conference. So the Manning Kubernetes Day here on Twitch. I was honored to be a part of that. So I'm giving it a type of conference, a name of, this is all just JSON here, a name of Manning Kubernetes and a location of, oh, it's on Twitch. Maybe this is URL or just me saying, oh yeah, it's on Twitch. And then I create a second piece of data here. And this is going to represent all the interactions that I do to manage my responsibilities with this Manning Kubernetes conference. So it's a type of interactions. I give it the ID. So this is kind of like a foreign key that corresponds to the conference ID that's passed in. Where do I actually get that from? Oh, I think it's just it's just a string. Anyway, and then events. So this is going to start as an empty array, and this is I think this is their way to do an empty array for JSON and Java. Like I said, I'm not a Java developer. My experience with the JSON APIs in Java are pretty shaky, but it's an empty array. Okay, let's go back up to main. So that's going to create those 2 documents just to get us started. The next thing I'm going to do is going to set up this transactions object. Now, this is what I'm going to use to actually start and perform and complete a transaction. And this is, again, this is Couchbase, so this is a Couchbase specific transactions.create, giving it a Couchbase cluster. And then I specify here the durability level. So how durable do I want this transaction to be? Now, I've got this set to none currently because my demo is just running on my local machine here. And so there's no replication involved. It's just one node. This is really not a production level of durability, but it's what I have to use for local development on one node. Other levels here is majority. So this is, wait until there's each write is available in memory on the majority of the replicas. So I'm replicating data to 1, 2, or 3 other nodes. Let's wait until the majority of those are there. So if it's 3, then wait until 2 of them are written, and that's good enough. The third one will still be written, but we don't have to wait on it. And then the next one is persist to majority. Wait until each write is available in memory and persisted to disk on a majority of those nodes. So again, if we're replicating to 3 nodes, we want to wait till it's in memory and on disk on 2 of those nodes. And the third one will get there eventually, but we don't have to wait on it. So these are kind of some trade-offs that we can do for giving us, making us feel strongly about this transaction is going to be durable enough, but we're also going to kind of trade off to make sure it's still pretty fast. Last one is majority and persist to active. You kind of see where this is going. Wait until each write is available in memory on a majority of replicas, and it's also persisted to disk on the active node. And this is a lot to take in, but remember back to the 3-node example. So it's written to disk on the main node, persisted to memory on a majority of the other replica nodes. And I say replica nodes. In Couchbase, every node it can do both. So it's just for this particular transaction. Okay. So these are different levels of trade-off in performance and just confidence and durability. And then after creating this object, I'm going to do a press enter to continue here. We'll see why that in a second. And now here's the actual transaction. So transaction run, and I assume this is what's called a lambda in Java. That's what I call them in .NET. This has a parameter of CTX. CTX is the transaction context. That's what I can use to interact with data while I'm inside of a transaction. So let's start the transaction. This is right here. This is starting the transaction. I'm going to get, again, CTX, to get two pieces of data, the conference and the interaction. Remember, I created these earlier on. I initialized them earlier on. And get those pieces of data and then put them into an in-memory, in Java memory JSON objects, because I'm going to make changes to them. And what I'm going to do is I'm going to add another interaction. So this will be the first one. Add an interaction to it, and I'm going to increase the count of follow-ups in the main document, the conference document, by 1, and get right now as my last interaction date. I'm kind of doing this a little bit backwards, right? I'm modifying the conference first, and then I'm adding the actual item to the events array. So it's I'm going to I got this. I have this wrong here. I was playing with this earlier. This is the first one I want to put in. So I'm going to submit to the CFP. No, that's a comment. Gosh. So my first interaction is submit to the CFP, which is often the first interaction I have with the conference is, hey, I'd like to speak at your conference. Here's some topics that I can speak on. And so it's the same date as I'm also putting into the main conference document. Normally this is 2 steps, but I'm making it all inside a transaction, so it's going to be atomic. It's going to all succeed or all fail. Then I'll just actually do the replacement in the database. So I've got that modified JSON data and place in the database. This comment stuff will come back to that. And then at the end of the Lambda, right here, the transaction is now committed. The Java application is saying, go ahead and commit. I've done everything I want to do, done. And that's implicit here. I could also explicitly say commit. So if I wanted to do this inside some logic, for instance, I could do that. Okay, so that's it. Let's take a look at the Couchbase data right now. It was on the screen here a second ago. This is the demo bucket in Couchbase. I don't know how well you can read this. Let me zoom in a little more. So there's nothing in here right now. No data in this what's called a bucket now in Couchbase. Absolutely nothing. Okay, let's go back to Visual Studio. I'm going to run this console program, Control F5. So you see it down here at the bottom. Let me just zoom in a little bit here. Connecting to Couchbase. And okay, creating the initial documents and creating transaction object. Now I'm waiting for a key press, waiting for an enter. So before I do that, let me go back over to the data. Retrieve these documents. So this is the momentum document, or no, sorry, not momentum, Manning document that contains information about the Manning Kubernetes conference. Momentum's another conference that I'll be presenting at. Starts with M, so sorry about that. But Manning Kubernetes conference, and it's located in Twitch. Okay, and those interactions here, which you can see corresponds to Manning Kubernetes. No events, just an empty array right now. Also, you'll see this little _TXN document here. This is some data that the transaction's using to keep track of things. So in the future, these are going to become basically hidden, but for now, you get a little peek behind the scenes. So, all right, so let's go back to the Java console. We're going to actually press enter and get our transaction going. And there it is. Zoom in here. You can see updating conference, updating interactions document, transaction complete. Back to the UI. Here we are again. Here is the interactions document. You can see here that it's got one event in it now, and that's submitted to the CFP. And this is the date of it. So it's ending in 346. Over here in Manning, we have one follow-up now, one event, and the date, 346. So the latest interaction is the one I just put in there. Okay. Let's just do it again. So we'll go back here. I'm going to trash this console, and we'll comment this one, and we'll uncomment this one. So the next interaction is going to be delivering the presentation, which is what I'm doing right now. So I'll go ahead and run this again. Very exciting, watching a transaction in action. And press enter, and there we go. So zoom in here, you can see ran the transaction, updated conference, updated interactions. Back to Couchbase, refresh. 2 events in there now, delivering the presentation. And over here in the main document, follow-ups is now 2, because there's 2 total events now. And the latest interaction date has changed, 357. I didn't verify that, but I'm pretty sure that matches this. Yep, 357. There we go. So the interaction document now has 2 items in the event array. So this is all great. And again, everything's going dandy. It's all happy path. But what happens when we get that blue screen? What happens if something goes wrong right in the middle of the transaction? So let's go back here. Trash this again. And now let's try to put our 3rd item in there. This is going to be answering questions on Slack afterwards. If there was a Slack or Twitch chat, I guess, I'd be answering questions after the presentation's over. But I'm also going to uncomment this throw new illegal state exception. And I'll comment on this part because of the throw. And this is going to happen before the commit happens. So before we even tell the database, okay, I'm done, go ahead and commit, an exception is going to happen. It's going to basically cause my program to crash. I'm not going to handle this exception. So what's going to happen when I do this? So let's go ahead and run it, see what happens. So here's the console, and we're going to have to press enter again. There we go. Oh my, look at all that. Look at all that messy exception there happening. And at the end, it's just what we told it to do, emulating a rollback, right? That's the exception. So what happened to the data? Because I did make these 2 replace statements here. Replace the first one, replace the second one. So what happened to the data? Let's go back and look. Retrieve documents, retrieve, retrieve, retrieve. Data still seems to be in consistent state. Only 2 events still. And only 2 follow-ups here and the latest date there. So the data is still consistent. It is not a dirty read. Everything has been rolled back to the state it was before the transaction happened. So this is exactly what we want. And I know this is not very exciting because, nothing's happening. It's just staying consistent. It's nice and boring the way we want it. But let's peel back the curtain a little more here. Do we have time? I'm running a little short on time here. If you don't mind, I'm going to just go ahead and show this because it's such a cool little peek behind the scenes here. So this time, I'm going to take the exception back out, and we'll put this one back in here. I'm going to set a breakpoint right here. See this little red dot? That's a breakpoint right there on line 123. So after the first replace, but before the second replace happens, set a breakpoint. And now I'm going to run this in debug mode. So F5 instead of Control F5. Okay. So I'm going to press Enter to continue, and there we go. We hit the breakpoints. What I'm going to do now is I'm just going to straight up kill this process. Stop this process right there in the middle of the transaction. So no chance to handle that exception and to do a rollback or anything like that. So what does the data look like? Go back here, retrieve, retrieve, retrieve. It looks like we're in good shape. We've got 2 events here still, not 3. And this one says 2 follow-ups. Again, not 3 and not a different date. That's great. But let's look at something here. Notice this little metadata tab over here. We've got a whole mess of data in here in metadata, specifically this X adders section, X extended attributes. And you can see that there is some staged data here. So let me zoom in a little bit on that. Some staged data. There's a bunch of other stuff here. I'm not going to go into that, but this data has been staged. This is the new data I was in the process of updating. You see 3 follow-ups and a new last interaction date. So it's just kind of this mess that's left behind because I killed the process right in the middle of the transaction. So this was supposed to be staged, but we never got to the commit portion. So it's left behind some mess, right? No problem. Because remember I mentioned the cooperative model, which says that the next process that comes along, it's going to clean it up. And so just by saying transactions.create right here, this is going to kick off a background process that's going to look for stuff to clean up. And it's going to clean up any leftover data, again, outside of that expiration time. And you can adjust that expiration time to make it longer or shorter, but I think it's a minute by default. So I'm going to go ahead and just kick that off here. I should have done this earlier because it does take about a minute just to verify. But I'm not going to press enter. We're just going to let the background process run, and it's going to just check for any transactions that are not cleaned up yet. And if I could, I'd fast forward, but I can't do that. So I'm just going to have to sort of vamp a little bit. I'm seeing a comment here. Consistency is exciting from SL Hod. Yeah, it's very, very exciting consistency. It's not exciting. It's actually very boring if it's done correctly, which is what you want. You want a nice, boring, consistent data. You don't want the more exciting situation of data being in all different places and all different states. Or maybe you do. I don't know. Maybe you're weird like that, that you crave that sort of excitement, that sort of high-octane development where the data could be in any given state. Who knows? It's going to be a mess. No, we want it nice and boring. But good to see you in the chat there, SL Hod. Anybody else have any questions or comments, just drop them right there in the chat. I don't think they're going to appear on my screen, unfortunately, because, like I said, I'm logged into, I'm hijacking Manning's stream. On my stream, which is, I'll just take the chance to plug it here, Matthew D. Groves, that's 2 T's in Matthew. I'll put a link here in the chat even. Wait, that's not my chat room. So I'll put it right here in this chat room. Twitch.tv/Matthew D. Groves. Okay, there we go. And so I'd appreciate a follow there if you want to see some more exciting consistency. All right, I think we've probably given enough time. If not, something might go wrong. That's okay. We can deal with that. Hopefully you get the idea. Okay, so this is where my knowledge of Java lambdas kind of falls apart because it seems to be retrying, but why is it which makes sense, that's fine, but why is it retrying and doing the system out multiple times? I don't know. So maybe a Java person can tell me why that's happening. But it looks like transaction succeeded, so we'll go back here to Couchbase, retrieve this documents, and voila. Now we have the third item here, and this one has 3 follow-ups with the last interaction. Good. What about the metadata? All cleaned up. Xatters is now empty, nothing in there for staging. It's all clean, ready for the next transaction, the next staging, what have you. So this is one of those edge cases that I mentioned. I just walked through that, I killed the application right in the middle of a transaction. So, what if I killed it 1 line earlier or 1 line later or 1 microsecond earlier, 1 microsecond later? It's tough to go through all those edge cases to build an ACID transaction that gives you the ability to treat multiple operations as a single all or nothing operation. So that's really where the Jepsen testing and just the mitigation and doing the best that you can and keep improving along the way. Hey, I got a sub from SL Hod. Thank you very much for that, SL Hod. I appreciate that. Thanks for being here. So just a quick review of some of the trade-offs here with ACID, especially with distributed ACID. Use only when necessary. So here's one thing you shouldn't do. If you're using the repository pattern, that's fine, but don't wrap everything in a transaction by default. So target those specific areas where you need it. Remember the overhead. And so whether it's a 2-phase commit on the client side or enhanced durability on the server side or whatever, there's more overhead. So just remember that. It's not going to be as snappy with the transaction. And if you want it to be snappier, solve it with data modeling. Use an aggregate-oriented approach as much as you can. Consolidate as much as possible to avoid the need for a multi-document transaction. But in the end, though, don't be afraid. They exist for a reason. They're a tool. They're a safety net. Go ahead and use them if you need to. Just wrapping up here, I just want to make the point that NoSQL transactions in NoSQL distributed databases are still basically on cutting edge, and they're still evolving and improving and being tested. So what I just demoed for you is the Couchbase key value API, and I want to make this point so you don't make too many assumptions about Couchbase, is that if you're using the key value API of Couchbase, you can start transactions, you can perform updates and do reads and then commit. If you're using the SQL API or any of the other APIs that Couchbase has, like full text search and so on, you're not going to get a dirty read. Right? You're not going to read information that's in the middle of a transaction, but you can't use SQL to make changes in a transaction and roll them back, at least not yet. It's just not supported. It's something that Couchbase is still currently working to solve. Some more NoSQL database vendors that are also doing NoSQL efforts, so it's not just Couchbase. This is a widespread among NoSQL. Here's Mongo. To me, it's not 100% clear on how they're doing it. It is a server-side implementation, unlike the Couchbase's client side. So you got to really dig into the server code and the server documentation. But various sources have mentioned they're using something called Lampert clocks for timestamping and ordering operations, gossiping. So if you want to get into all the details of that, you can check out the white paper there on ACM. Check out that link up there. Cosmos DB from Microsoft. This is on Azure. This is an Azure only, cloud only document database. And they used to only support stored procedures for transactions. But this year they've introduced something called transaction batch, which you can use in your own client code to do something similar. Cosmos is limited to a partition key. I believe Couchbase is also limited to a single bucket. Bucket and partition key are a little different things, but basically you can't be transaction across multiple different partitions or collections or things like that. It is limited to 2 megabytes and 5 seconds maximum timeout and 100 operations. Those all seem pretty reasonable to me, I think. If you find yourself running up against those limits, you may want to rethink your data modeling, and that applies for Couchbase too. Although I think Couchbase's limits are a little more flexible. So Couchbase is probably limited to more like E5 or ish 5 megabyte per document, right? So you can have multiple documents, and I don't think there's any limit to operations, but there is a sensible ceiling, of course. But again, this just kind of reiterates the point of just only do it when you have to. I want to mention Cockroach DB. It is not a NoSQL database. It's a relational database, so it's a so-called NewSQL database, which is distributed, attempts to be a distributed relational database. It's kind of inspired by Google Spanner. That's their cloud-based offering. And this is, again, server-side. And the reason it's server-side here, at least one of the reasons, is that Cockroach is trying to be compatible with Postgres drivers. And so therefore, they can't go through and update all the Postgres drivers to handle Cockroach. That would be quite an undertaking. So they're just doing it server-side. And so again, you have to worry about things like clock syncing and all those server-side things I mentioned earlier. And if you're doing this on your own data center, the database, if one of them gets outside the clock's limits, clock skew happens too much, you can shut down the whole database, so that can hurt availability if that happens. If you're using their cloud offering, it might not be as big of a deal because they have more control in that situation. But if you're running a data center, that's something you have to worry about for sure. All right, let's wrap up here. They say you only remember 3 or 4 things vis-a-vis any given presentation. So here they are, Neo. Now, you may not need transactions as much in NoSQL as you do in a relational setting. So don't forget that. The answer may not be transactions, it may be aggregation, and not taking the same exact approach as you do with relational. So NoSQL and ACID exist together now, and just in general, NoSQL is maturing. This session has been about the rise of ACID, but there's also been tremendous advances in security and integration, reporting, analytics, deployment. So if you've dismissed NoSQL in the past, I think it's worth a second look now. And the answer to why NoSQL is expanding. The reasons that exist in the first place still apply. So trade-offs that improve scalability, high availability, and flexibility. But now you have NoSQL maturing and you get ACID transaction capability, along with all those other things. If you want to go down the rabbit hole, you might want to take a screenshot of this right now, because I'm not going to paste all these into the chat. But Jepsen has a lot of material on consistency. If you want to read up more about that big tree, all those definitions mean. There's a video here from Graham Popel. I hope I'm saying his name right. It's an introduction to Couchbase transactions. He's one of the engineers that's working very hard on transactions at Couchbase. There's a great stuff there. I wrote an ACID blog post a while ago, even before Couchbase introduced transactions, because I wanted to convey that ACID isn't all about transactions and what does all the letters mean in ACID. Couchbase publishes a huge number of benchmarks there, and these are true benchmarks. They're not marketing benchmarks. These are true internal build benchmarks. And this will show you, if you go to that link directly, it'll show you kind of the overhead that transactions involve. So you can compare that to the other tab on that same web page that shows without transactions. There's a design document if you want to look into all the decisions that went into the design of transactions there. Hey, Code with Sean. Thank you. I appreciate it. Thanks for hanging out with me for a while. And the last one there is a white paper available at berkeley.edu about high availability transactions. Okay. And you can also contact me, of course. This is a picture of me when I used to wear suits and leave the house. But this is what I look like in 2020. So you can reach me on Twitter. Here on Twitch, I mentioned this a couple times, Twitch/Matthew D. Groves. That's my personal email address. Feel free to email me about transactions, Couchbase, whatever. Happy to talk with you. If you want to find my lame attempt at Java coding, it's all there on GitHub. GitHub/mgroves/don'tdropacid. Hey, thank you for the follow, XBBLVR. You don't see it on the screen here, but you follow my channel. I appreciate that very much. And there's a free event coming up in October. 3 days, free event called Couchbase Connect. A lot of stuff, including the transactions I talked about, will be covered here. But all the deep dives into NoSQL use cases and what Couchbase is doing. I've also heard there's going to be some great swag and prizes available there. I know because I'm kind of seeing all this stuff take place behind the scenes, like a Saturn V Lego rockets and Raspberry Pis and cool stuff like that. Again, totally free to sign up. Please use this link here, because if you sign up with this link, I get credit for it, and I get a free pizza for each person who registers. Not really. I wish I did. That would be cool. But I really appreciate if you use this link here to sign up for this free event coming up in October. I want to say thank you very much to Manning. Thank you very much, everybody who's hung out and checked this video, and especially those who have been commenting, asking questions. It's Friday. It's the weekend, so thank goodness. But I appreciate you all hanging out with me here. I hope you enjoyed it. And if you have any questions, drop them in the chat here. I'll hang out for a few more minutes. But at that point, I'll just shut down the stream and hand it back over to Manning. Again, I really appreciate everybody at Manning letting me do this. So I'm looking at the chat here. I'm not seeing any questions come up. Appreciate SL Hod and Code with Sean for chiming in during the session. Let me just put this slide back up on here just in case it wasn't up there long enough for you to get this link to sign up. I'll be presenting at this event as well, not on transactions. I'm going to leave that to our amazing engineers to talk about those. But I'll be presenting on some .NET specific topics like background processing, back to threading again, and just generally upgrading your .NET application. So look forward to those. If you liked my presentation, you can go check those out at Couchbase Connect. If you didn't like my presentation, good news, because it says 60 here, but I think it's up to 100 now. 100 sessions of great technical content, and not just by Couchbase employees, but by Couchbase community speakers as well. I'm really happy that we've got a lot of our community members and customers and developers participating in this event as well. Okay, well, since there's no more questions coming in, I'm going to wrap it up here. Just say thank you one more time to Manning, and thank you for watching, and I hope you all have a good weekend.